Okay, here we go. Recording. Okay, so in your experience with algebra, you've added, subtracted, multiplied polynomials. What happens when you divide them? That's what gives rise to a rational function. So maybe you guys don't know why rational functions are called that. They're called rational functions. I need my styles. Hold on. Here we go. Perfect. Okay. So the called rational functions because it's a ratio of two polynomial functions. That's what a rational function is. It's a ratio of two polynomial functions. Notice the word rational. Ratio. That's where it comes from. So it's a ratio of two polynomial functions. So for example, I'm going to work out this set here with you guys, and then I'm going to have you guys in your groups work out the other sets. So if I were to do f1 of x divided by g1 of x, you have x minus 2 over 2x plus 3. That is a rational function. Because think about it. Is x minus 2 a polynomial? Yeah. If it has more than one term, it's poly, right? And the terms are x raised to the power, right? X by itself is x to the 1 power and 2 h is constant. So it's really a polynomial. Yes. In fact, actually called a binomial because it has two terms, right? And it's a ratio in this table. Do you have one on top of the other? Yeah. That's what a rational function ever is. Just to recap, what is a polynomial in case you guys are a little iffy on that. I did talk about in the video, but maybe you guys didn't catch it, or I didn't maybe explain it very well because I was doing it at 5 in the morning, I think. What is a polynomial? It says right here, and that's really hard to read. But a polynomial is when you have a real number times x raised to the whole number. So when you have x raised to the whole number, and a collection of those terms, that is a polynomial. So, like for example, if I have like 2x cubed plus x squared, that is a polynomial. But what if I change that x squared to like x to a -4 power? Is -4 a whole number? No. So this ceases to be a polynomial function because then it becomes 1 over x4, which actually is rational, by the way.
What happened?
No, I'm saying for a polynomial, you need to always have x and a whole number as the exponent. Okay. That's all.
So it can't be negative?
Was that can't be the exponent can't be negative, and it can't be a fraction either.
Right.
Yeah. So that's what's happening with polynomial. But a rational is a ratio of the two, right? It's a ratio. Okay. So anyway, so let's go back to this one I just wrote. There we go. Okay. So here's what you're going to do today. You're going to add, subtract, multiply, and divide whichever pair I give you. I'm not going to ask you guys to do all 8 of these pairs or 9 of these pairs. That's too much. I'm going to assign a pair to each group. So you guys will have to do groups of 3, right? This is perfect. We have 15 people. This is perfect. 3, 3, 3, 3, 3. So I'm going to give each group one pair to work with. But I'm going to do the first pairs just so you see what I'm expecting you guys to do. So it says here, make your own prediction of the shape of each new graph and draw a quick rough sketch on your paper. And again, you're going to combine these by addition, subtraction, multiplication, division, right? So you're going to actually be making 4 graphs.
Wait, per thing?
4 graphs for one of the pairs I give you. Yeah, you're only going to work with one pair, but I'm going to make 4 graphs from each pair. Right? So again, we have that. Then once you draw a quick sketch, you're going to check with your teammates, see if you guys have the same thing. You're going to use graphic calculator or Desmos. So if you have a laptop, that's fine. You could use Desmos and kind of just talk about what you see, right? And then also in the next page, so I gave you guys enough space down below, and also on the next page as well. So what does the new graph look like? What happens if you do the expression in different orders? Why would things look differently? Also has with domain and range. So let me model the process for you guys right now. So what were the equations I had? Let's see here. I'll do it right here because I have a little more space. Okay, here we go. So my equations were the following. Okay. Actually, let me just delete that. Okay. So I have f1x. Yeah, f1x was x minus 2 for me. and G. And you guys can write this down somewhere else. I mean, you'll have enough space, or you can just watch. It's totally fine too. So you're going to do this. You're going to graph f1x plus g1x, f1x minus g1x, f1x times g1x, f1x over g1x. Okay, let's think about what's happening here. What happens if I add f to g? What do I get if I add f to g? What would happen if I use
3x plus 1.
Yep, you get 3x plus 1. Yep. Excellent. Thank you, Hunter. How about if I subtract? What do I get? Careful with the subtraction part. You might want to put parentheses around this, each one. What happens when you subtract? What do you guys get? Negative x minus 5. Yeah, careful there. When I multiply, what's going to happen? What else I multiply is what do I get? Keep going. Keep going. Minus 6. So it's 2x squared negative x minus 6. Okay. And you just put one on top of the other for this one, right? Okay. Now I'm going to do quick sketches. Again, you guys are going to do very rough sketches here. Very rough sketches. And actually, let me do it right next to each of these here. Before we do that, let's talk about it. What kind of graph would this be? 3x plus 1. What kind of shape would that be?
Linear.
Linear. Oh, next one. Oh, sorry.
Also linear.
Also linear, right? How about this one, x squared plus x? It's a parabola. Actually, it's probably easier to back it up this way, but you see it's a parabola. And this one's a rational function. That one's going to be a little tricky. But let's do these first three. I think we can do it pretty quickly. And here we go. What's the slope and y-intercept for the first one?
The slope is 2.
No, for this one.
Over that one. Oh yeah. 3.
Yeah. So again, I'm doing a rough sketch, kind of like that. Oh, x minus 2. No. For these here. How about x minus? Oh, let me hide this. Here we go. How about negative x minus 5? So probably something like that, roughly. Yeah, it goes down. Yeah, crossing the y-axis at negative 5. How would you go about graphing the parabola? Is it opening up or down, by the way, your parabola?
Opening up.
Up. And where's it crossing the x-axis?
Oh.
Yeah. And what's the y-intercept here, by the way? Negative 6. Good. Okay. So again, rough sketch, right? Now this one's kind of tricky. What's going to happen here? You have to do something called asymptotes, which you guys will talk about later today. What you want to do is you want to find what makes the bottom 0. What would make the bottom 0 here? Or sorry, if I set the bottom equal to 0, let me rephrase my question. I didn't phrase that very well. If I set the bottom equals 0, what would x equal? A negative 3 over 2. Because you can't divide by 0, right? Because that would be undefined. So what you do is you draw a dashed line at negative 3 halves. You can make a table if you want. Like, what if I were plugging like 0, for example? If I plug in 0, what do you get?
Negative 2.
Negative 2 over what?
Oh, 2 over 3.
Okay, so probably over here. What if I plug 2 in? What do I get? What does the top become, guys, if I plug 2 in? 0 over 7, so 0. Okay. What if I plug in a big number? Like, say, 10. It's not too big. 8 over 23. What if I plug 100 in? I know that's getting a little crazy. Over 203. So take a look at 98 over 203. I know it's really hard to do here, but 90 over 203 is roughly plus a fraction, not plus a decimal. It's getting closer to what 90. Oh, 0. Yes, 98 over 98 would be roughly what fractions would be. Well, 1/2, basically. Yeah, it's close. I know it's kind of complicated, but it's close to 1/2. So what's going to happen is the graph will get close to 1/2 off to the right. Likewise on the other side, if you graph more on the other side, I know, let me just clear my screen now. It's getting really messy. Here we go. Again, I have x minus 2 over 2x plus 3. Add this, right? Add some points here and here. That's 1/2. So the graph kind of looks like this. So the vertical asymptotes, that's just a boundary that you can't cross for x, was x equals -3/2. So you set the denominator equal to 0. And do that again. Here we go. Set the denominator equal to 0 and solve for x. Okay. On the other side, if I were to plug in, say, I don't know, -2, what happens if you plug in -2? What do you get?
1 or -1.
You get -4 up top. What do you get down below?
Oh, yeah, I'm sorry.
-1, so you get 4. So it's actually going to be a little higher. And the graph will look like this here, because what if I were plugging like -10? If I plug in -10, what do you got up top, guys? Over -17, I think.
Yeah.
So it's getting close to -1/2. Sorry, +1/2. So you also have something called the horizontal asymptote as well. I'm gonna help you guys with this part because I know it's a little tricky. But that's your rough sketch. Then you state domain range for all these, and then you're good at that point. So going back to what I had previously. So again, I had f1x plus g1 at f1 minus g1 at f1 times g1 at f1 over g1. So you're going to state domain and range. Now for lines, that's pretty easy. What's the domain for all lines? It would be what? If you had a line, what would you say your domain would be? How with the range? Yeah, all real numbers. Yeah, that's easy. For a parabola, what would be the domain for a parabola? Any parabola. All real numbers, but how would you do the range? Yeah, you gotta find the vertex, and if it's above, I'm guessing y is greater than that number, less than if it's going down. The other ones of rational function are a little tricky. You have to exclude whatever makes the bottom 0, and also you have to sometimes exclude the range depending on what's happening with the asymptotes. So anyway, that's what we're working on right now. So I'll come around and assign each. Actually, I'll just tell you right now what you guys are gonna do. So this group, you guys are gonna do F2 and G2. In the back, you guys do F3 and G3. In the middle, you guys do F4, G4. Off to the right, near the front, you guys do F5, G5. And the way back, you guys are doing F6, G6. Okay, so you're gonna do the same exact thing. Draw a sketch. You have enough space in your paper of F1, or sorry, adding, subtracting, multiplying, dividing. Okay. Yeah, go ahead. And then you're gonna state domain range. I'll help you guys out. Okay. And then we'll move on to the rest of the notes after that. That's all. Yeah, go ahead. Yeah. Let me do this one more time with you guys. So I think you guys need to see this in action one more time because these are a little complicated. So let's move on to 62. And then after that, we have maybe just a couple more examples, and we're done with the notes for today. You guys can get some homework. And we get at what, 12:05, right? Okay. So we'll see how far we get. Maybe we don't get to all the examples today, but at least we talked about rational functions in more detail. So let's look at part A of 62, right? So you're asked to estimate their sum, difference, product, and quotient functions before using a graphing tool. So for parts A through E, sorry, A through D, sketch a careful graph, make a note of the shape, domain range, blah, 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 right? So let's do it right now. Oh, here we go. Okay, so this one's easy, just adding these guys. So what happens? You have x cubed minus 2x minus 2, right? Just adding p and q, right? That's easy. Part B, you're subtracting. Gotta be careful here. X cubed minus 3x minus 1 minus x minus 1. You just get that. Part C, you're multiplying. So you have the FOIL, which would be x4 minus 3x squared minus x cubed. Sorry, let me back up a little bit. You get x cubed minus, sorry, you get x4 minus x cubed. Then you get negative 3x squared plus 3x. And you get negative x plus 1. x4 minus x cubed minus 3x squared plus 2x plus 1. So that's kind of a crazy polynomial. And then D, excuse me, D is going to be x cubed minus 3x minus 1 over x minus 1. Now, let's actually focus on D right now, because we haven't really talked much about how to graph these just yet. Those are a little complicated. Let's focus on D. What makes the bottom 0 here? Exactly. So you can't plug in 1. So you draw this. You draw this little boundary. It's called a vertical asymptote. It's a boundary we just can't touch. Now let's make a table and pick numbers to the left and to the right of this boundary. Like, let's say I plug in 0 and say I plug in 2. If you plug in 0, what do you guys get? Plug in 0 both top and bottom. Work it out. Tell me what you get when you plug in 0.
1.
Negative 1 at the top. And how about down below?
Negative 1.
What's that together? Negative 1 over negative 1?
Just 1.
Good. Excellent. So you have that. Okay, let's plug in 2. If you plug in 2, okay, careful with this one. You get 8 minus 6 minus 1, which is what?
1.
1. And what do you get on the bottom? 2 minus 1.
1.
So you still get 1. Okay. All right. Let's plug in, let's say, now this is where it gets a little confused. That's where you have to use a calculator. If I plug in 10, you have 10 cubed minus 30 minus 1. And down below, you have 10 minus 1. What's 10 cubed? 10 times 10 times 10. It's a pretty big number, right?
Is it 1,000?
It's 1,000, yeah. 1,000 minus 31, which is 969. 9. So that's like a pretty big number, right? It's like way up here somewhere. Let me erase some stuff. It's a really big number. Like way, oh goodness, hold on. Okay, got it. Sorry about that. Like way up here somewhere. Let me erase this. Okay. So the graph probably might look like this. And when you get closer to that vertical asymptote, it shoots down or shoots up forever. If I were to plug in, say, I don't know, negative 10. Place that at negative 10, right? So it becomes plus 30. Yeah. Now that's negative 1,000 plus 29. And down below is negative 11. It's still a positive number. Still, that's negative 971 divided by negative 11. So it's still a positive number, like way up here somewhere. So it's probably doing something like this also. And again, I don't expect you guys to be totally accurate with this, but it's more of just a guessing. I mean, more of like an estimate of what you're trying to, and you can always check with Desmos. I'm going to plug in Desmos right now to see what happens. Ben, go ahead. Great question. This one won't have one. Yeah, let's talk about it. This is actually fantastic discussion point and great way to end today's class. Thank you for bringing that up. So this one does not have. Actually, Ben, that's probably one of the best questions I've heard this year. Thank you. That's really good. Does not have a horizontal asymptote. Here's the reason why. X cubed minus 3x minus 1. Oh, goodness. What's going on here? Okay. So what's the whole point of a horizontal asymptote? It's basically what y approaches as x goes towards infinity, or x goes towards negative infinity. So when x gets really large, that's what a horizontal asymptote does. So let's look at one of the examples that one of you got, like for example, this table here, Sophia Hunter and Charlotte. You guys had, which one was it?
Second.
Yeah, so they had x plus 3 over 5x minus 9. Take a look at it. When x gets really large, right? That's gonna be like, let's say x is like 1,000. The plus 3 is kind of small compared to 1,000, right? The minus 9 is pretty small compared to 5,000, right? So overall, if I plug in 1,000 for x, right? If x equals 1,000, that's like 1,003 over 4,991. Overall, that fraction gets closer to 1/5 because you use exponents. The exponents that connect these x's are hard number. So basically, the leading coefficients help determine the false asymptote. But look at the one I just did right now. So you plug in 1,000. What's 1,000 raised to the third power? A really big number, right? In fact, actually, it's a billion. It's 9 zeros. Down below, pretty big too, but it's just 999. So you're doing a billion over a large number. Sorry, over a reasonably large, but not too large. If you think about it, it's not leveling off. When this degree is higher than the bottom, y won't level off. And that's the reason why you don't see horizontal asymptotes. There is a generalization that comes with it, which we're not ready to talk about today. We'll talk about on Wednesday. But there's a generalization that comes with it that you can look at the exponents for both top and bottom and compare them. And that will kind of give you a hint as to whether you have a horizontal asymptote or not. If the degrees are the same, it's always going to be the ratio of the coefficients. And if it's actually the bottom is higher, the bottom has a higher exponent than the top, it's actually 0. If the top is higher than the bottom, then it's just there isn't one. So we're going to stop there for today. I think that's pretty much covers. We could talk about the rest of the stuff next time. The homework you guys should be able to do just fine. A lot of it's review and stuff that we talked about today. So it should be pretty straightforward. I'll put the solutions up as well. I'll give you guys a 10-second head start about that for lunch. So